Dear students, welcome to Tungal online classes. Let us continue with the average power in an inductor circuit. Yes, so let me consider an inductor of inductance L connected to the alternating source of voltage given by V is equal to V naught of sin omega t. Yes, in the inductor circuit we know the current lags the voltage by 90 degrees. So, I can write I is equal to I naught of sin omega t minus of pi by 2. Yes, mathematically the instantaneous power in the AC circuit is given by P is equal to the product of instantaneous voltage and instantaneous current. So, I can write P is equal to V into I. Yes, let us substitute the values here. P is equal to V is nothing but V naught of sin omega t. Yes, and the current I can write it as I naught of sin omega t minus of pi by 2. Yes, so this is the equation for the power. Then let us simplify this. I can write P is equal to V naught into I naught sin omega t. So, this sin omega t minus of pi by 2 I can write it as minus of sin pi by 2 minus of omega t. Yes. So, let me simplify this again. I can write this as V naught I naught sin omega t. This minus I will write it outside. Sin pi by 2 minus of omega t is nothing but cos of omega t. Okay. Again, so this I can write it in the form of sin 2 omega t. Yes. So, for that multiply and divide it by 2, I can write P is equal to minus of V naught I naught divided by 2 into sin omega t into cos of omega t. Yes. So, this I can write it as P is equal to minus V naught I naught divided by 2 into this I can write it as sin 2 omega t. Okay. So, this is the expression for the instantaneous power at any time t. Okay. So, the average power during one complete cycle of the alternating current. So, to get that average power, we shall integrate this. So, P average is equal to integrate this equation between the limits of 0 to t. Okay. So, integrate between the limits of 0 to t, where t is the time period of one complete alternating cycle. Yes. This I can write it as minus of V naught I naught divided by 2 into sin of 2 omega t into t. I will integrate this term with respect to time between the limits of 0 to t. Yes. So, let me write P average is equal to V naught is constant, I naught by 2 is constant. So, let us take them outside. Minus of V naught I naught divided by 2 integration between the limits of sin of 2 omega t into dt. Okay. Integration of a sine function over one complete cycle which repeats continuously, that is equal to 0. So, this term becomes equal to 0. Hence, the average power during one complete cycle when we have the inductor in a AC circuit, that is equal to 0. Yes. So, this is how we can prove the average power in the one complete cycle of the alternating current in a inductor circuit is equal to 0. When an AC circuit is containing a pure inductor, as the current flows through the inductor, because of the changing current through the inductor, there is magnetization and demagnetization of the inductor. Okay. As and when the current changes the direction, there will be flux induced in the inductor which magnetizes the inductor, and when the flux reduces, that demagnetizes the inductor. Okay. So, how the magnetization and demagnetization of the inductor occurs during one complete cycle of alternating current, that we shall observe here. Okay. So, let me consider an inductor of inductance L which is connected to the alternating voltage V is equal to V naught of sin omega t. Yes, and as we know, the current lags the voltage by pi by 2 radians. The variation of the current and voltage that we have drawn here, along x axis I am plotting the time, along y axis I am plotting the current, voltage and power. Okay. Let us divide this one complete cycle into 4 quarters of t by 4 time period. Okay. So 0 to t by 4, t by 4 to t by 2, t by 2 to 3t by 4, and from 3t by 4 to t, where t is the time period of one complete cycle. Yes. So let us observe what happens during each quarter. All these quarters, the phenomena are represented by figure 1, 2 and 3 and 4. Yes. During first quarter of the cycle, the current increases from 0 to maximum. This is the current curve. Okay. And this green color curve is it is corresponding to voltage. As the current increases from 0 to maximum, the flux, the EMF induced in the inductor also increases from 0 to maximum. Hence, the magnetization of the inductor coil occurs during the first quarter, that is from 0 to t by 4. Yes, during the time period of 0 to t by 4, the current through the inductor increases from 0 to maximum. The flux in the inductor also increases from 0 to maximum. Hence, we observe the magnetization of the inductor coil during the time period of 0 to t by 4. Okay. So during this part of the cycle, the voltage is reducing. The voltage is reducing as the current increases. Okay. But the voltage is also positive, the current is also positive. Hence, the product of these two, voltage and current, that is power is also positive. Okay. So what happens here? Actually, the inductor is getting magnetized by the energy supplied by the source. Yes, what is happening? The energy is given to the inductor by the source to magnetize that inductor. Yes, so that is indicated by the positive power. Yes, so during the first quarter, the energy is supplied to the inductor by the source. Okay, then next what happens during the second quarter, that is from t by 4 to t by 2 time period, the current through the inductor, that is getting reduced from maximum to 0. Okay, and we can observe here in both these cases during first quarter and during second quarter, the direction of the current is from A to B. Okay, so the direction in during first and second quarter, the current is from A to B. Hence, the magnetic field lines are also having a similar direction here. Okay, so during the second quarter, the direction of current is same, but the magnitude is reducing from maximum to 0. Okay, the magnitude is reducing from maximum to 0 again. So whatever magnetic flux was developed during the first quarter, that is getting depleted here, that is reducing. Yes, so actually in second quarter, what is happening? Whatever energy was stored in the inductor in the form of electromagnetic energy, that is again given back to the source. Yes, the energy is given to the source by the inductor. So the flux is reducing, the flux around this inductor is reducing, which is shown by the less number of magnetic field lines here. Yes, then next during the third quarter, you can observe here the current is changing. Yes, so then during the second quarter, observe here the current is positive, the voltage is negative here. So the power, which is the product of positive current and negative voltage, that power is negative. Yes, so this negative power indicates the energy is given back to the source by the inductor. Yes, then during the third quarter, the direction of current is reversed. So during the third quarter, the direction of current is from B to A. Yes, hence the magnetic flux is also induced in opposite direction, which is shown by the direction of these magnetic field lines. Yes, so during the third quarter, the current is increasing from 0 to maximum in opposite direction. So this will also induce the EMF in the coil. So this will magnetize the coil in a opposite direction. Yes, so the flux starts building as the current increases. So exactly at 3t by 4, the current is maximum, the current is maximum, hence the magnetic flux induced is also maximum here. Yes, so during T by 2 to 3T by 4, the coil gets magnetized from 0 to maximum value, but the direction is opposite. Case number 1 and case number 3, the directions are opposite, the process is the same. Yes, because the direction of the current is opposite. Okay, then during this third quarter, the current is negative, the voltage is also negative. So the power of negative current and a negative voltage, that is again positive here. So this positive power again indicates the energy is given to the inductor by the source. Yes, then during the fourth quarter, that is the last quarter here, the current magnitude is decreasing from maximum to 0. So as the current decreases from maximum to 0, the magnetic flux also reduces. So during the fourth quarter, the inductor gets demagnetized. The inductor gets demagnetized. What actually happens here? Whatever energy was stored in the inductor during the third quarter, that energy is again given back to the source. Hence, the flux reduces. Okay, so during the fourth quarter, the current is negative, the voltage is positive. The product of negative current and positive voltage, that will be again negative here. So the power cycle during the fourth quarter, that is in the negative region, which indicates during the fourth quarter energy is given back to the source by the inductor, which causes demagnetization of the inductor. Yes, so observe this graph here. During 2 quarters the power is positive, and during 2 quarters the power is negative. Positive power indicates the energy is given to the inductor, negative power indicates the energy is given back to the source by the inductor. Hence, over one complete cycle, the average power is equal to 0. Okay, so this is how we obtain the average power is equal to 0 by magnetization and demagnetization, alternate magnetization and demagnetization for every quarter of this alternating current cycle. Yes, that is why we get the average power over one complete cycle through an inductor circuit equal to 0. Yes, let us continue with the concept of the average power in a pure capacitor circuit. Yes, so for that let me consider a capacitor of capacitance C, which is connected to the alternating voltage V is equal to V naught sin omega t. Yes, and we know in a pure capacitor circuit the current leads the voltage by pi by 2 radians, and its equation is I is equal to I naught of sin omega t plus of pi by 2. Yes, and the instantaneous power at any time, that is given by P is equal to the product of instantaneous voltage and instantaneous current. Okay, so that we can write it as V naught of sin omega t, and what is the equation for current? That is I naught of sin omega t plus of pi by 2. Yes, and this I can write it as P is equal to V naught into I naught into sin omega t plus of pi by 2. This is nothing but cos of omega t. Yes, and this can be written as P is equal to V naught I naught. I will multiply and divide by 2. I can write it as into 2 times sin omega t into cos of omega t. So instantaneous power can be written as V naught I naught divided by 2 sin of 2 omega t. Okay, the total power for one complete cycle can be obtained by integrating this equation between the limits of 0 to t, where t is the time period of this alternating cycle. So P I can write it as integration between the limits of V naught I naught divided by 2 sin of 2 omega t with respect to time. Okay, I will get this equation P is equal to V naught I naught by 2. I will take it outside. V naught I naught divided by 2 integration of 0 to t sin of 2 omega t into dt. Okay, so this is the harmonic function. So I can write it as the integration of sine 2 omega t over one complete cycle of alternating current is 0. So, I will get the average power in one complete cycle of alternating current when we have pure capacitor, that we get it as 0 here. Whenever a capacitor is connected to alternating source of voltage, the current changes its direction continuously. Okay. Due to this continuously changing current, there is a charging and discharging of the capacitor. Yes, how this charging and discharging of the capacitor occurs during the one complete cycle, that we shall observe. Yes, so here let us divide this one complete cycle of alternating current into 4 parts, that is from 0 to t by 4, t by 4 to t by 2, t by 2 to 3t by 4, and from 3t by 4 to t, where t is the time period of one complete cycle. Okay. So, let us consider the first quarter from 0 to t by 4. Okay. During the first quarter of the cycle, yes, so that is represented here. During this first quarter of the cycle, the energy is supplied from source to the capacitor. Okay. So, initially when the charge on this capacitor is 0, that charge gradually increases from 0 to maximum value. Yes. So, the plate A gets positively charged and plate B gets negatively charged at the end of first quarter, that is during the time of t by 4. Yes. So, the charge gradually increases from 0 to maximum, hence the potential developed, that also increases from 0 to maximum voltage. Okay. So, that we can observe here during the first quarter, the current is decreasing from maximum to 0. Okay. When the capacitor is completely charged, the current will stop. So, that is the value of the current at t by 4. Yes. And at t by 4, observe this voltage curve. Yes. So, this indicates the maximum value of voltage. Okay. When the voltage is maximum, it is understood that the charge stored in the capacitor is also maximum. Yes. So, during this first quarter of the cycle, the current is also positive and the voltage is also positive, and we know the instantaneous power is given by the product of instantaneous voltage and instantaneous current. During the first quarter, the current is also positive, the voltage is also positive, hence the product of this current and voltage, that is again positive here. So, this dotted line which indicates the power is on the positive side of the graph. Okay. So, what happens during first quarter here? The energy flows from the source to the capacitor. Yes. Hence, the capacitor gets charged. The charge on the capacitor increases, the voltage across the capacitor also increases to the maximum value. Yes. And the power consumed is positive, which indicates the power is given to the capacitor from the source. Energy is transferred to the capacitor from the source. Yes. So, that is what happens during first quarter of the cycle. Yes. Then during the second quarter, what happens? Whatever energy was stored in the capacitor during the first quarter, that energy is given back to the source. Yes. Hence, observe here, during the second quarter from t by 4 to t by 2, the direction of current is changing. The black color line, the current curve is changing its direction. So, we can observe the current is changing the direction here also. Initially, it was moving in a forward direction, but during the second quarter, the direction of the current is reversed. When the direction of the current is reversed, the charge stored on the capacitor plates, that gets depleted. Yes. So, the charge on the capacitor plates reduces. So, whatever energy was stored on the capacitor, that is again given back to the source. Okay. Hence, during the second quarter, that is from t by 4 to t by 2, there is a discharging of the capacitor. The charge stored on the capacitor will be lost because energy will be given to the source from a capacitor. Okay. So, graphically we can see here, from t by 4 to t by 2, the current is negative and the voltage across the capacitor, that is decreasing from maximum to 0 here. Yes. So, at this point, at the end of half of the cycle, that is after the 2 quarters, at t by 2, when the time is t by 2, the voltage is 0, which indicates the current, the charge is also 0. Okay. Hence, if I consider the power, voltage is plus, but the current is minus. Hence, the product of positive voltage and negative current, the power is negative during second quarter of the cycle, which indicates during second quarter energy is given back to the source. Yes. Then next, during the third quarter, the direction of the current is same, but the magnitude of the current is decreasing from maximum to 0. Now what happens, as the current continues to flow through the capacitor in the same direction, the capacitor gets charged. Yes, see here, at the end of a second quarter, actually the capacitor did not have any charge, but as the current continues to flow, there is development of the charge with opposite polarity. Yes, compare these two figures here. Here the current was moving in forward direction, so plate A was positively charged and plate B was negatively charged. But observe the third figure here, the current is moving in opposite direction, hence the polarity of the capacitor plates is reversed. Plate A is getting negatively charged and plate B is getting positively charged. Yes, so at the end of third quarter, that is at time is equal to 3t by 4, the capacitor will have the maximum charge. Okay, when the charge is maximum, the voltage is also maximum here, but the voltage is in opposite direction, as we can see from this graph. Okay, what happens during t by 2 to 3t by 4? Current is also negative, voltage is also negative. So the product of negative current and negative voltage, that will give you the positive power. The positive power again indicates during the third quarter of this cycle, the energy is given to the capacitor from the source. Yes, that is the meaning of this positive power during third quarter. Yes, then again during the last quarter, you can see the current is changing its direction again. Yes, so it is crossing the x axis here, so it is changing the direction. We can observe the current is moving again in a forward direction. Okay, because of this changed direction of the current, whatever charge was accumulated on the plates of the capacitor, again that starts getting reduced. Yes, so the capacitor charge gets reduced, hence during this part the capacitor is getting discharged. Yes, so at the end of time period t, at the end of one complete cycle, again the capacitor charge will become 0 here, which is indicated by the value of V, which is equal to 0 at a time t is equal to capital T. Yes, so during this cycle, the voltage is negative, the current is positive. Yes, the product of this negative voltage and positive current, that is again negative. So the power is negative during the fourth quarter of the cycle. Yes, so this negative power indicates the energy is given back to the source. Yes, during the discharging of the capacitor, what happens? The energy is again provided to the source by the capacitor. Yes, so during all these 4 quarters, 2 times the energy is given to the capacitor. Remaining 2 quarters, the energy is given back to the source by the capacitor. Hence, the average power, observe here, I have 2 quarters of positive powers, remaining 2 quarters of negative power. So the average power during one complete cycle, that is equal to 0. Yes, so this is graphical representation that the average power during one complete cycle of alternating current through a capacitor circuit is equal to 0. Yes, so because of this changing current, there is continuous charging and discharging of the capacitor. To maintain the current of I through this LCR circuit, there is some work done. Okay, let the rate of this work done to maintain the current through the LCR circuit, let it be given by dW by dt, which is nothing but power. Okay, so dW by dt, it is the product of V and I, which are the instantaneous voltages and current values. Okay, and this can be written as, so from this I can write small work done to maintain the current through the LCR circuit for very small duration of the time, dW I can write it as VI into dt. Okay, and let us substitute the values of V and I can write it as V0 sin omega t into I is nothing but I0 of sin omega t minus of phi into dt. Okay, so this is the small work done. So I can write this as dW is equal to, let me simplify this, I will write it as V0 I0 into sin omega t. This is sin omega t minus of phi, I can write it as sin omega t cos of phi minus of cos omega t into sin of phi. Okay, into dt I will write. Yes, then multiply this term inside, I will get it as dW is equal to V0 I0, I will multiply this inside sin square omega t into cos phi minus of V0 I0 sin omega t into cos omega t. So this dt I will write it inside cos omega t into sin of phi into dt. Okay, so this is the simplified form here. Then, so this is the work done to maintain the current through the circuit for very small duration of time dt. Okay, so the total work done, to get the total work done to maintain the current through the circuit for one complete cycle, that can be obtained by integrating this over one complete cycle. That is, so the total work done is integration of this RHS with respect to time between the limits of 0 to t. So I will integrate the RHS, that is V0 I0 sin square omega t cos phi into dt minus of integration between the limits of 0 to t V0 I0 sin omega t into cos omega t into sin of phi into dt. Okay, so both integrations are between the limits of 0 to capital T, where t is the time period of alternating current cycle here, which indicates one complete cycle. Okay, let us simplify this here. V0 I0 cos phi is constant, I take it outside. V0 I0 cos phi integration between the limits of 0 to t sin square omega t into dt. Okay, minus of here V0 I0 is constant, sin phi is constant, that I take them outside. V0 I0 into sin phi integration between the limits of 0 to t. This is sin omega t into cos omega t, I can write in the form of sin 2 omega t. Okay, sin 2 omega t divided by 2, the divided by 2 I take it outside. Okay, with respect to time I am integrating. Okay, so then the integration of the sine function over one complete cycle, so that is equal to 0 here. So I will remain with the work done is equal to V0 I0 cos phi integration between the limits of 0 to t sin square omega t, I can write it as 1 minus of cos 2 omega t divided by 2 into dt. Okay, and if I simplify this, I get the total work done is equal to what? V0 I0 2, I will take it outside, divided by 2 into cos phi integration between the limits of 0 to t 1 into dt, separately we shall integrate them, minus of integration between the limits of 0 to t cos of 2 omega t into dt. Again the integration of cos 2 omega t over one complete cycle, this term is 0. So I will remain with W is equal to what? V0 I0 divided by 2 into cos phi integration of 1 with respect to t is equal to what? T, and the limits are from 0 to t. Okay, and let us substitute the limits. I get it as V0 I0 divided by 2 into cos phi. First let me apply the upper limit, capital T minus of lower limit 0. So I get W is equal to W is equal to V naught I naught cos phi into T whole divided by 2. Okay. So, this is the work done to maintain the current through the LCR circuit for one complete cycle. Okay. Then by the definition of power, power is equal to what? Work done divided by time taken. Okay. And let us substitute the value here. So, I can write P is equal to W is nothing but V naught I naught into cos phi into T whole divided by T, 2 times of T. So, this T get cancelled here. So, I can write it as a P is equal to this 2, I can write it as the square root of 2 into square root of 2. So, I will write it as a V naught divided by root of 2 into I naught divided by root of 2 into cos phi. Okay. Why I am writing it like this? Because I can write the same term. V naught by root 2 is nothing but V RMS and I naught by root 2 is nothing but I RMS into cos phi. Okay. This is the expression for the average power during one cycle through the LCR circuit. Okay. So, here we call P is nothing but the true power. Yes, P is the absolute power or the true power, and the product of V RMS and I RMS, that is V RMS into I RMS will give me the virtual power. This is called a virtual power. Okay. This is the expression for the power, average power through the LCR circuit for one complete cycle of alternating current. Yes. Next we have power factor. We have seen for an LCR circuit, the power is given by I RMS into V RMS into cos of phi. Okay. In this this complete value, that is power, this is called the true power. This is called true power, and the product of this I RMS into V RMS, that is called apparent power, apparent, or it is also called virtual power. Okay. So, by this expression we can write cos phi is equal to what? P divided by I RMS into V RMS. Okay. So, this is the ratio of true power or the absolute power and the virtual power through an AC circuit. Okay. And if you remember the impedance triangle, yes. So, impedance triangle is something like this. So, here along x axis I have R, here I have XL difference of XC, whichever is greater that we can take, and here if I have Z. Okay. Z is the vector sum of R and difference of XL and XC, that is the reactance. Okay. So, here we have the phase angle is phi. The same vector can also be written as V here, VR. So, let me write O, A, B. So, here we will have VL difference of VC. Okay. From this impedance triangle also we can write cos phi is equal to what? R divided by Z. So, that is the ratio of adjacent side and hypotenuse. Okay. So, in another way, the power factor can also be defined as the ratio of the resistance and the impedance in an AC circuit. Okay. So, what happens for pure resistor circuit? For pure resistor circuit, we have R is equal to Z. So, cos phi will be equal to what? Cos phi will be equal to 1. Okay. So, when cos phi is equal to 1, that is the maximum value of the power factor. So, when cos phi is equal to 1, the power consumed will be maximum. Okay. So, the maximum power is consumed when we have pure resistor circuit. Okay, because cos phi value will be equal to 1. Okay. Similarly, if we have pure inductor or capacitor circuit, the phi value will be equal to what? 90 degrees. The phase difference between the voltage and the current will be 90 degrees, either plus 90 degrees or minus 90 degrees. In both the cases, cos phi is equal to 0. Okay, when cos phi is equal to 0, the average power in inductor is equal to 0, as well as in capacitor also the average power is equal to 0. Okay, so that already we have seen with analytical and graphical solutions. Okay, so this is about the power factor. For resistor circuit, power factor is maximum, and for inductor and capacitor circuit, the power factor is equal to 0. Hence, the average power over one complete cycle of a capacitor and inductor circuit will be equal to 0. Yes. Next, we shall discuss an interesting concept of Wattless current or idle current. Okay. So for that, let us consider an AC circuit in which the current is IRMS and the voltage is VRMS. Okay, and let us assume at time t that voltage VRMS is at phase angle difference of phi with respect to IRMS. Okay, then the power consumed in this circuit is given by P is equal to what? VRMS into IRMS into cos of phi. Okay, where cos phi is the power factor in that circuit. Yes. Now let us resolve this IRMS along the direction of VRMS and in the perpendicular direction of VRMS. Okay, what I will do? Let me project it on VRMS here. So this component will be the adjacent component. So here I can write it as IRMS cos phi. Okay, adjacent component is IRMS cos phi, and the perpendicular component, that is the opposite component, that will be IRMS into sin phi. Okay, the RMS value of current can be resolved into two components. One is along the direction of VRMS, another is in the perpendicular direction of VRMS. Okay, now the total power will be sum of the power because of this IRMS cos phi and IRMS sin phi. Okay, the power consumed because of this component, that is IRMS cos phi, is given by P1 is equal to VRMS into IRMS cos phi, and the angle between this VRMS and IRMS cos phi is what? That is 0, because both are parallel to each other. So here I will get the power factor is equal to what? Cos 0 degrees. Okay, because both are along the same direction. So P1 I will get it as a VRMS into IRMS into cos of phi. Okay, next we shall see what is the power consumed because of the perpendicular component IRMS sin phi. Okay, so that I will write it as P2 is equal to what? Voltage into current component, that is VRMS into IRMS. This component is what? IRMS sin phi into what is angle between these two? That is 90 degrees. So here I will have cos of 90 degrees. Okay, cos 90 degrees is equal to 0. Hence I will get P2 is equal to 0. Okay, the total power is equal to what? P1 plus of P2. So that power is equal to VRMS IRMS into cos phi. Okay, so this is the same as this value here. Yes, so from this I can observe whatever power is consumed, so that is to maintain the component of IRMS cos phi along the direction of VRMS. Okay, this current component, we don't need any power to maintain the current component, that is IRMS sin phi, which is in the perpendicular direction of VRMS. Okay, this component of the current, that is IRMS sin phi, which does not require any power for its maintenance, is called Wattless current or idle current. Okay, we don't need any power to maintain the current in the perpendicular direction of VRMS. Okay, so whatever power is given, that is to only maintain the current along the direction of VRMS. Okay, so this perpendicular component, this component of the current does not need any power for its maintenance,